All right, today we're going to explore a data structure that's fundamental, but also, surprisingly powerful. I'm talking about the circular linked list. It's a really simple concept on the surface, but it has some seriously clever applications. So let's get right into it. First up, a question. Have you ever stopped to think about how your computer can possibly juggle so many things at once without completely freezing up? You've got your browser, music playing, a dozen other things running. How does it give each one just enough attention to keep everything running smoothly? Well, a big part of that magic actually comes down to the elegant little loop of a circular linked list.
Okay, so before we can really appreciate the circle, we kind of have to understand the straight line, right? On one side, you have arrays, super rigid, but man, are they fast for just grabbing an element. That's O of 1 access. On the other side, you've got your standard linked lists. They're way more flexible, but finding something can be a real slog. That's O of N, slow. This whole trade-off is the perfect setup for where our star player, the circular linked list, comes in and really shines. So what if we took that standard linked list and just made one tiny tweak? Well, that brings us right to our main event, a list that has no end.
Yeah, a circular linked list is pretty much exactly what it says on the tin. You know how in a normal linked list, the very last item points to, well, nothing? It just points to null, the end of the line. But here, instead of stopping, that last node points right back to the very first one. And just like that, you've created this continuous, unbroken loop. And this visual makes it super clear. Check this out. We've got our nodes, 3, 5, and 9. Now, in a regular list, that last node, 9, its next pointer would just be empty, null. But here, nope. It loops right back to the beginning, to node 3. And that's what completes the circle. There's literally no end to the road. And here's what's so cool about that loop. Think about it. Since there's no official beginning or end, you can literally pick any node you want as your starting point, and you're guaranteed to be able to visit every single other node in that list. For certain kinds of problems, that is an absolute game changer. Okay, so how do we actually go about building one of these things? Turns out, there are two main ways we can construct the circle. So on the left here, you see a singly linked circle. Think of it like a one-way street. You can only go forward, from one node to the next. But on the right, we've got a doubly linked version. Now this is a two-way street. Each node doesn't just know what's next, it also knows what's before it. That means you can travel in either direction around the loop, forward or backward. Super flexible. Right. A data structure isn't much good if it's static. We need to be able to change it. So how do we actually add or remove nodes from our circle without, breaking that crucial loop? Let's dig in. Okay, so let's say we want to insert a new node at the beginning. And I say beginning because, there isn't really one. It's basically a three-step dance. First, you create your new node. Easy enough. Second, you make its next pointer point to what used to be the first node. And for the grand finale, you find that very last node in the chain and tell it to point to your new one. Let's see what that actually looks like. So here's our before picture. We've got our little circular list just humming along, and this new node, we'll call it T, is waiting to join the party right at the front. And boom, just like that, it's in. You could see node T is now pointing to what was the first node, and crucially, the node that was at the end of the chain has updated its pointer to aim at T. The new node is integrated, and our circle is still perfectly intact. Now for the really important part, performance. How fast is this? Well, inserting a node at either the beginning or the end is what we call constant time, or O1. That is incredibly fast. Why? Because we don't have to go searching through the whole list. We just have to update one or two pointers, and we're done. Deletion, though, that's a different story. To delete a node, you first have to find it, which might mean you have to look through the whole thing. So in the worst case, that's linear time, or O of n. All right, this is all very clever, I get it. But why should you care? What's the point? Let's connect this back to some stuff you use every single day. Remember that multitasking question from the start? Well, here's the payoff. Operating system schedulers, they live and breathe this stuff. A circular list is perfect for giving each application a little turn with the CPU. Your browser gets its time slice, then the music player, and when it gets to the end, it just naturally loops back to the beginning. No need to check and reset. It's the same beautiful logic for multiplayer games, cycling through players' turns. Really, it's the perfect tool for any process that needs to just go round and round and round. So to sum it all up, the huge advantages,
You can start anywhere, and it's just tailor-made for these cyclical, repeating tasks. The downsides? Well, they're a little trickier to implement than a plain old linear list, and you have to be really, really careful. One tiny mistake in your code, and you can easily create an infinite loop, which is, well, it's exactly as bad as it sounds. All right, now just when you think you've wrapped your head around it, computer science always has another trick up its sleeve. Let's take a peek just beyond the basic circle.
So remember that doubly linked list, the one where you can go forward and backward? It's great, but it costs you extra memory for that second pointer in every single node. What if you could have that two-way travel without the extra memory cost? Well, that's where something called an XOR linked list comes in. It is a wild idea that uses some clever binary math to cram the addresses of both the previous and next nodes into a single space.
And this is basically the magic formula behind it. The link for each node stores the bitwise XOR of the previous address and the next address. Then, to move through the list, you just XOR your current location with that stored link value, and it magically gives you the address of where you need to go next. It's an incredibly clever memory-saving trick, but yeah, it's definitely a bit more of a headache to implement.
And that brings us full circle. It all started with such a simple idea, didn't it? Just take the end of a list and connect it back to the beginning. That one tiny change created this incredibly powerful tool for everything from operating systems to games. It really makes you wonder, what other simple, elegant ideas are just waiting out there to completely revolutionize the way we handle data?